Hello, good morning once again. In this video lecture series for analog circuits and design. Right. So today's topic that we are going to start is BJT small signal analysis. Now see the name itself saying it is a small signal analysis. Right. Now before that lecture what we have studied is common emitter configuration, common base configuration and common collector configuration. Alright, and what we have studied, we have studied its current factors. For example, if it is common emitter configuration, then its current amplification factor is beta. If it is common base, it is alpha, and if it is common collector, then it is gamma. Is that? And then before a few lectures, we had a discussion about the relationship between those alpha, beta, and gamma also. Is that? Now, as if we know that BJT, if I want to use it as an amplifier, then compulsory I have to make one terminal common. Yeah. And then I can use the BJT as an amplifier. So that's why now we are going to start with its analysis. How I can model BJT. Right? How can I model BJT means if I'm using BJT, look at this, if I'm using BJT in amplifier, it means what first thing I need to do, I need to bias the BJT first. Is it? I have to bias the BJT and then I have to configure this in one of the configuration, maybe common emitter or maybe common base or maybe common collector, whatever. If you bias the BJT and configure it common emitter, then it will be BJT common emitter amplifier, or maybe if it is common base, then BJT common base amplifier, or maybe common collector amplifier. Now if I want to analyze those amplifiers, if I want to analyze those, then I have to model them. Is it? I have to model them compulsory. Then only analysis is possible. So somewhere I have to model them, and for modeling of the BJT, we will use two-port network. Is it? The two-port network theory is well known to everyone. I will write two-port network. So that will be the base for our analysis. Is it? And that was the base to have those configurations also. Is it? You remember we had the transistor has only 3 terminals, but if it is a two-port network, then I require 4 terminals. Is it? Look at this. This is a basic two-port network. So transistor has 3 terminals. Two-port network requires 4 terminals. Then what idea we have used? We made one terminal common. Yes, one terminal is common. So one terminal is common. So that's why which terminal is common? If it is emitter, then it is common emitter amplifier. If it is base, common base. If it is collector, then common collector. That's what it is. Now let us start with what do you mean by that small signal analysis? The small signal means generally we know. Look at this small signal. Small signal means obviously it is low frequency. So whenever there is a signal with low frequency, what we refer it? We refer it as a small signal. If the frequency is high, then it is higher frequency signal. Is it? So basically small signal means small frequency signal, the signal which has very small frequency. That's what. Now from where the frequency component comes in, why this frequency entered into our scenario? Is it? We are in transistor, we are in some network laws, we started with two-port network, then in between, from where I'm getting this frequency component and why? Is it? Let me tell you, if it is BJT, look at this, if it is BJT, we know that we have two junctions. Is it? Look at this. If I'm saying this is emitter, this is base, and this is collector, then collector base junction, emitter base junction, two junctions are there. So if I have junction, then I must have junction capacitance. Look at this, I must have junction capacitance. is it? And whenever capacitance is there, how can I define capacitance? What is the property or what is the parameter that I can well explain the capacitance? By its capacitive reactance, Xc. You remember that? What is the equation for Xc? Yes, everyone knows that it is 1 divided by 2 pi f into c, is it? Or generally people write 1 divided by omega c, whereas omega is equals to what? It is 2 pi f, right? So 1 divided by 2 pi f multiplied by c, that is capacitance. Now see, if this frequency is very low, then what will happen? This capacitive reactance, obviously it will be very high. Right? If the frequency is low, then obviously the capacitive reactance will be very high. Why? It is because the frequency component, it is in denominator, so it is an obvious thing. Now come towards the transistor once again. Here I have two capacitances. Like this, I have junction resistors also. Look at those junction resistors are also there. Let me call it as an R1 and R2. Don't get confused between this R1 and R2 and the biasing resistors R1 and R2. They have nothing to do with each other. They are completely different. Even I am using those R1 and R2 as just in vague notations, is it? I don't know what, some name has to be given, so that's why I'm writing R1 and R2. Now see, two resistors are there, two capacitances are there. This resistor, the junction resistance I'm talking about, and a capacitor, junction capacitor, generally they are in, not generally I say, they are in parallel. See, resistors, a junction resistance and junction capacitance, they are in parallel, are in parallel. So when junction capacitance and junction resistance are in parallel, one important thing is this resistance. Look at this, it's a resistive, it's a pure DC resistance, and it is independent. It is independent of frequency. No matter what the frequency is, if frequency is high, it will never affect. If frequency is low, it will never affect. So it is independent of frequency. Another important thing about this junction resistance is it is very small. This is very small. Those are two properties of that junction resistance. What are those? Junction resistance is very small and it is independent of frequency, no matter what the frequency is. Now, this small resistance is in parallel with a capacitance. The capacitance which is frequency dependent. Obviously, if it is a capacitor, it is frequency dependent. How the capacitor is frequency dependent? That's why. Look at, that's how capacitor is frequency dependent. We have explained this. If frequency is very low, the capacitive reactance is very high. Now consider low frequency component when frequency is very low. As if low frequency, this capacitive reactance is very high. Then how can I draw this parallel equivalent circuit then? One thing, look at this. One resistance, that is junction. I'm still in junction. JR we have written. So this is what junction resistance in parallel with junction capacitance. Now at very low frequency, look at this, at very low frequency, this junction capacitance, is it, or capacitive reactance of a junction, right? This capacitive reactance means, generally how can I define it? It is an impedance offered by the capacitor. Yes, I can. It is an impedance offered by the capacitor. Roughly I can say it is an impedance offered by the capacitor. That is what Xc is. Xc is what? Impedance offered by capacitor. Now as if I am treating this capacitor C as an impedance offered by the capacitor, then let me replace this capacitor. Let me replace it with a small impedance. That small impedance I will treat it as an XC. Let me draw a small impedance. What is that now? This is XC. What is that XC? It is a component of JC, junction capacitance. Is it? So now junction capacitance is replaced by XC, and at low frequencies XC is very high. XC is very high at lower frequencies. Now at lower frequencies, what is the picture? The picture is a small value of resistance is in parallel with a higher value of resistance. So small value of resistance in parallel with high value of resistance, what our thumb rule says, the equivalent resistance will be very small. Yes, we know the thumb rule. When small value of resistance, if it is in parallel with large value of resistance, the equivalent resistance is always a small value of resistance. Is it? So it means at lower frequencies, junction impedance is always small. Is it? So at at lower frequencies, the junction impedance is very small, and that's why at low frequencies we refer it as a small signal module for transistor. We call it as small signal module for a transistor. That's what the only reason. Now okay, sorry for the interruption. Let us start once again. At lower frequencies, junction impedance is very small. That's why it is small signal module of a transistor. Now, so we are talking only about the small signal. We are talking only at the lower frequencies. Right. So if I want to analyze the BJT, then obviously don't think only for lower frequencies. I need to think about the higher frequencies also. So if I want to analyze BJT amplifier, then at lower frequencies I will use a model which is called hybrid model. And at higher frequencies, okay, let me write it now here. At higher frequencies, the module which is used to analyze the BJT amplifier is pi module. Right. And in this voltage amplifier thing, what we will do, we will discuss lower frequency analysis, that is we will use hybrid model. Right. And when we go into the higher frequencies, then we have to use this pi model. That is what maybe this is your 4th chapter and this is your 5th chapter. Like this, we are going to cover all the analysis regarding BJT amplifier. So at lower frequencies, BJT uses hybrid module. There are some parameters related to hybrid module, and at higher frequencies I must use the pi model. Now it is an obvious that if I want to analyze the BJT, compulsory I need to have the reference of two-port network. So without the reference of two-port network, it is not possible to analyze the BJT at lower frequency or maybe at the higher frequency. So compulsory I need to take reference for two-port network. So now before starting with lower or higher analysis of BJT, I must understand what is two-port network. So let us start with what is the two-port network. Two-port network is a simple analogy where every circuit or any circuit can be modeled in this scenario: two terminals at the input side and two terminals at the output side. And now we are not in BJT amplifier, we are in BJT. So as if we are in BJT, I can't model it in two-port network. I said many times that BJT has 3 terminals. Then what we have done? We make one terminal common, is it? And that's why now BJT can be modeled as 2-port network. This is what my BJT now. See, one, this is second terminal. Look at it. This is also second terminal which is common, and maybe this is a third terminal. So now 3 terminals are there. BJT is this. Yes. Now it is okay. The thing is, now if it is BJT, then here somewhere we have input. Now every 2-port network has, at the left hand side we have input, at the right hand side we have output, is it? Now here, if it is an input side, it must have input impedance, that is Zin. What is that Zin? It is input impedance. It is input impedance. Now here between 3 and between 2 we have output, though there must exist output impedance. So what is that Z out? I am writing here, Z out is output impedance. So now total 4 parameters are there with me roughly if I am treating BJT as a 2-port network. So what are those 4 parameters? First parameter is input voltage. It's not voltage all the time, it is just an input. So for our reference I am considering voltage because we are in voltage amplifier. We have to study, we have to discuss BJT as a voltage amplifier. So that's why I am writing voltage. Is that input? So this is what input voltage. V out. What is that V out? V out is output voltage. So now 4 parameters: input voltage, output voltage, input impedance and output impedance. 4 parameters are there if I model BJT in 2-port network. So let us arrange it. Now if it is input impedance, let me draw it at the input side. Let me draw it at the input side. Now I have to show some input voltage. So let me show this as an input voltage. So this is what my input side. I will call it as Zin, and this is input voltage. So I have to call it as V in. Right. So it is an input side. This is what this part I am covering. Yes, this part is done. Now see, one terminal is common between input and output. So let me draw that common terminal here. Let me draw the common terminal as like this is what common terminal. Now output voltage and output impedance has to be shown in the circuit. So let me show that this is what output voltage. A voltage component is shown like this. So now what is this? This is also voltage. This is VO. Is it, or what I can say V out? And here this is output impedance. What is the notation? It is Z out. Yes, it is Z out. So now 4 parameters are there. 1, 2, 3, 4 terminals. 1 is common. 4 parameters I have inserted. Right? And this is called, look at this circuit. What this circuit is called? It is called general 2-port equivalent circuit. General 2-port equivalent circuit. This is called general 2-port equivalent circuit. It means any circuit, any electronic circuit can be modeled into that kind of 2-port network. Right? You take BJT amplifier, yes, I can model it in this fashion. You take any circuit, you take BJT oscillators, BJT multivibrators, you take any circuit using BJT, I can model it with this scenario, 4 parameters, and it is called general 2-port equivalent circuit. Now by using this general 2-port equivalent circuit, how can I analyze BJT amplifier? That's what the question is. Now Again, see, the topic for this lecture is small signal analysis, is it? And I have concluded with one thing, that this is what two-port network. By using that two-port network analogy, I can analyze all the amplifiers, right? So if I'm saying I can analyze all the amplifiers, first I need to enter into the amplifiers, then I have to discuss the amplifier, and then I have to apply this analogy to the amplifier, right? So let us start with any one amplifier, maybe common base, common emitter, or common collector. Let us start with the amplifier, and then when starting at the analysis of amplifier, use this analogy of two-port network and then start the analysis, is it? So let us start with any amplifier. Mostly I'm using common emitter amplifier. I'll tell you the reason why. I think we had a discussion about why every time I'm considering common emitter. If not, then I'll tell you why, right? Or maybe in next lecture we'll continue with those things.